my dear students. Today we will learn about divergence of r cap by r square. We already learned about this divergence, and in one of the sections we have already done the problem divergence of r cap by r square. Now there is a peculiarity for this function r cap by r square and its divergence. In this section we will check what is the peculiarity of this function r cap by r square and its divergence. Okay, so the function is given like this. That means let I can write here, let vector v equal to r cap by r square. Okay, that means if you plot this function, the function should be like this. This is the point. Then they are all flowing out from this point. Okay. Okay. If you plot this function, it's from this point it's flowing out. From this diagram itself, you get a picture that this function has positive divergence, right? Because divergence is a measure of flowing out from a point. For this function 1 by r square r cap, it is like this. It's flowing out from this point like this. That means the figure shows a positive divergence. Okay? I write here positive divergence. Okay? Now, we can find out its divergence using our expression for divergence. Especially for easiness, we use the expression for spherical polar coordinates. Divergence in spherical polar coordinates. Okay. So, del dot v in spherical polar coordinates. Now, this del dot v equal to 1 by r square, okay, 1 by r square d by dr of r square vr. Okay, here this vector v has only r cap component, vr only. There is no v theta and v phi. Okay, so you can write this vr r 1 by r square. Okay, here vr equal to 1 by r square. You can substitute here, then you get r square by r square. You know that r square by r square equal to 1. That means 1 by r square d by dr of 1. What is differential of 1? 1 is a constant, so its differential is 0. Okay, so this gives you gradient in spherical system, and its divergence with vector v gives you 1 by r square d by dr of r square, 1. Okay, 1. This is equal to 0. Now we just confused. Why? Because here from the plot itself we see that its divergence is positive divergence. But if you find out the divergence using the expression, you get it as zero divergence. the theorem. Okay. So, for applying this Gauss divergence theorem, consider a closed surface S V dot dA, and here we assumed this surface as a sphere of radius capital R. Okay, sphere of radius capital R. Now what happens to this function? So you can put here surface integral, and for V 1 by R square R cap, because this capital R is the radius of the sphere. Okay, we need the vector on the surface of this sphere. So it is 1 by R square R cap dot R cap R square sin theta d theta d phi. R square sin theta d theta d phi. Since these two R cap dot and R cap dot making up, you will get here similarly in this part. This R is capital R square, because we are taking the sphere, surface of the sphere. Radius of the sphere is capital R. Okay, so this is the expression. These R squares cancels out, and you have now the integrals like this. Integral 0 to pi for theta, polar angle. Okay, 0 to pi sin theta d theta. Then integral 0 to 2 pi for azimuthal angle, 0 to 2 pi d phi. Here you get 2 pi, here you have 2. So what do you get? You get 4 pi. Okay, so if you decide to apply Gauss divergence theorem and done this one part, surface integration over closed surface. Okay, it gives you like this. This is equation 1, this is equation 2a. Now, in order to finish the Gauss divergence theorem, you have to find out the volume integral also. Right? That means volume integral of del dot V. This time this is our spherical coordinates d dot. Okay, so what you get here? Here we already found that this del dot V is 0 from 1. Okay, del dot V is 0. So this gives you 0. This is equation 2V. Now what happens? Gauss divergence theorem states that the surface integral of a vector over a closed surface is equal to volume integral of divergence of the vector. So this surface integral should be equal to this volume integral. Okay, but you can see that here the surface integral gives you 4 pi, but the volume integral goes to 0. So it looks that Gauss divergence theorem get violated. So some problem with this function r cubed by r square. Okay, that means 2a not equal to equation 2a not equal to equation 2b. Okay, Gauss divergence theorem. Gauss divergence theorem violated. Okay, that is we start with a by r square, and from its geometry we feel that this function have positive divergence like this. Then we move on to its mathematical part, and using spherical coordinates we find out its divergence, but unfortunately we get zero divergence. Geometry predict positive divergence, but its mathematics shows zero divergence. Then in order to verify the situation, we move on to applying Gauss divergence theorem. There we see again that its surface integral gives you a positive value, but its volume integral goes again to 0. So, the Gauss divergence theorem get violated. Okay? So, this function, this r cap by r square is a particular type function. We have to address this function with some other distributions. That is the problem with this divergence. Okay, so just remember all these things. If you find out divergence of r cube by r square, it will end up in some type of discrepancy like this. Why this happens? Because this function r cube by r square is singular at r equal to 0. Why? Because you can see that at r equal to 0, that means at the origin, at r equal to 0, this function blows up. Infinity. 1 by 0 means infinity. Okay? So, at r equal to 0, the given function v blows up. So, the function is the divergence of r cap by r square is 0 except at r equal to 0. That is the discrepancy. The entire contribution to the divergence coming up from the single point at r equal to 0. Okay? The function r cap by r square blows up at r equal to 0. Blows up at r equal to 0. Okay. So, its divergence is 0 except at r equal to 0. Except at r equal to 0. At this r equal to 0, it has a definite value. Okay? The entire contribution to divergence comes out from r equal to 0. Okay, so this function is not behaving just like an ordinary function. That is the problem. Okay, our function, this divergence of r cap by r square, not behave just like an ordinary function. It has a definite value at a particular point, otherwise it is 0. For example, for this physical example, for this is physical example. density of a point particle. Density of a point particle. The density of the point particle has value only at its location. All other points it has zero value. Density has zero value. But its volume integral. What is the volume integral of density? It is mass. Okay, volume integral of density is mass. But it has a finite value for its volume integral, mass. Okay, so this is a physical example, density of a point particle. Density is 0 except at its location. Okay, still the volume integral has definite value. Volume integral has definite value as its mass. Okay, so to address these type of functions, we can use a new distribution which is known as Dirac delta function. Okay, next we will learn about this Dirac delta function. Now, Dirac delta function is not an ordinary function. Actually, mathematicians call this as a generalized function. Okay, this is known as generalized function. Generalized function or distribution. Okay, generalized function or distribution. Okay, because we already found that in the case of divergence of r cap by r square, there is some discrepancy and it blows up at origin and all those things. So, in this context, this Dirac delta function is not an ordinary function because it has high value at some particular point in space and it dies out very fastly in all other points. In that sense, it is a particular type of function. So, mathematicians call this as generalized function or distribution. Okay, now we will learn about its one-dimensional version. Okay, one-dimensional Dirac delta function. One-dimensional Dirac delta function. One-dimensional Dirac delta function. Okay. In this context, in the case of one-dimensional Dirac delta function, the function depends only one independent variable. Okay, and the notation used is del of x. Okay, this notation is used to represent Dirac delta function. Del of x. Okay, this del of x, the properties of function is written inside this curly bracket. Del of x equal to 0 for x not equal to 0. Okay, del of x equal to 0 for x not equal to 0, and this del of at x equal to 0. Okay, del of x equal to 0 except at origin, and this is equal to a very high value or infinity at x equal to 0, and the area under this curve is unity. That means integral minus infinity to plus infinity del of x dx equal to 1. Area under the curve equal to 1 or unity. Okay, this function is called Dirac delta function. I can show here the mathematical plot just like this. Okay, this is del of x and the independent variable is plot like this. This is x. Now we can see here that del of x equal to 0 except at x not equal to 0. At x equal to 0 it is infinity. So very high value I can show here. Somewhere here it's very high value, and it goes like this. Okay. This area under this curve is unity. Okay, area is 1. This function is called one-dimensional Dirac delta function. So this function has very high value at origin. This is origin. This is 0. Okay, this is origin. This function has high value at x equal to 0 and nearly 0 as x increases. It goes to 0 very fast. And so area under this curve is also a unity. If all these properties hold a function, it is called Dirac delta function. Now you can compare this with the earlier discussion of density of point particle. Well, we see that in the case of the density of a point particle, it has a very high value at the point where it locates. And if you take its volume integral is always a finite value. That means a point particle has a definite mass always. That is what happens here also. Here this is one-dimensional function, so this integral is only one variable. Okay, and this area under this curve is 1, unity. This is called one-dimensional Dirac delta function. Now, actually what is this Dirac delta function? You have some other problem to accept the concept. So for that we have certain some more definitions by the mathematicians. One of them is this Dirac delta function the limits of sequences of functions of rectangles, functions of rectangles. These functions of rectangles are represented by Rn of x with height n and width 1 by n. Do you get a picture? That means if you consider rectangle that rectangles have height n and corresponding width 1 by n. Ultimately, it tends to Dirac delta function. As n tends to infinity, the series converges to Dirac delta function. I can draw here the figure. See, this is the x-axis. Okay. Now we can write two rectangles here, rectangular functions. First one is r1 of x. For r1 of x, height is 1 and this width is also 1 by 1, right? So I can show here the position. Somewhere here, suppose this is 1, this is 2. Okay? 1 and 2. This is height. For height 1, width is also 1. 1 by n means 1. Okay? So I can write here its positions like this. This is minus half and this is minus half. Okay? Total this width is 1. Now I can draw here the rectangle like this. Width is 1 by 2. Width is 1 by 2 means here it is minus 1 by 4 and here 1 by 4. So I can draw like this. For n equal to 3 and width 1 by 3 it gets again narrow. And as n tends to very large number, and even in this case n equal to 10, this thing goes to very sharp peak. Okay, this kind goes to very sharp peak. Okay, so for large n, this series, this rectangles, sequence of rectangular functions converge to Dirac delta function. Okay, that means as this increases again, this thing goes like this, like this. For large n, you will get a figure like this. This is here also Dirac delta function. Okay. Similarly, you can consider this Dirac delta function as the limits of sequence of functions of isosceles triangles. Okay. This is all about rectangular functions. Next thing is isosceles triangular functions. Okay. So sequence of functions of the limits of sequences of functions of isosceles triangles with height n and base 2 by n. Okay, base 2 by n. Here also you can draw the figure like this. as usual, I show here this is n equal to 1 and this is somewhere here n equal to 2. Now 2 by n, base is 2 by n. For n equal to 1, base is 2. Okay, so I can put here 1, here is also 1. This is minus 1, this is plus 1, total base is 2. Okay, like this. Okay, this is T1 of x. The next case is for n equal to 2. For n equal to 2, you can see that base is 2 by 2. 2 by 2 means 1. Okay, so here you have minus half, here plus half, and the isosceles triangle is like this. Okay, this is T2 of x. Okay, like this, if you increase n, you will get more narrow triangles, and this goes to a very narrow peak. That is called the limits. Okay, so for large n, this sequence tends to a Dirac delta function. This sequence converges to Dirac delta function. Okay. Now I think you can get a picture of what is Dirac delta function in one dimension. In one dimension means it has only one independent variable. In this case, del of x has only x. So it is called one dimensional Dirac delta function. Okay. In this here we give here at the origin this function has infinite value. In practice, infinity means very large value at the origin, and it goes 0 fastly as we move away from this origin. That is what we meant by this expression. And the area under this curve is always 1. In this case, this is about one-dimensional Dirac delta function. Now we can check its property. Okay. The first property. First property is let f of x is an ordinary function. Ordinary function. Okay. Ordinary function means continuous function. Okay, ordinary function or continuous function. Continuous function. Okay, so we consider a function such that it is continuous and ordinary function. There is no blows up or something like that. Okay, and if you multiply this function with the Dirac delta function, f of x equal to f of x into del of x. Okay, f of x into del of x equal to 0 except at x not equal to 0. Why? Because Dirac delta function is 0 except at x equal to 0. Okay, so that means this f of x delta x equal to 0 for x not equal to 0. del of x is 0. So this product always 0. So what you get from this? F of x delta of x equal to f of 0 delta of x, f of 0 delta of 0. If delta of 0, except that x not equal to 0, this is goes to 0, so this whole thing goes to 0, no problem. So you can write this thing, f of x delta of x just as f of 0 delta of x. Okay. Now we can do any integral. We already see that this Dirac delta function has a property. Area under the curve is always finite. Okay. We can check that here also. So integral minus infinity to plus infinity f of x delta of x dx. You can replace this f of x with f of 0. Okay. So you get here f of 0 integral minus infinity to plus infinity del of x dx. What is this integral del of x dx? This is area under the curve. We see that this is equal to 1 for one-dimensional Dirac delta function. Okay, so you get here f of 0. Okay, this is the one of the property of one-dimensional Dirac delta function. That means under integral sign, Dirac delta function helps to fix out the value of a function at the origin. You can see here that because we have a function f of x, ordinary function or continuous function, then if you find out this integral f of x del of x dx, it gives you the value of the function at the origin. Okay, this is an important result which you can frequently use while you doing problems. Okay, so under integral sign, Dirac delta function picks out the value of an ordinary function at the origin. Okay, this is an important property of one-dimensional Dirac delta function. Under the integral sign, it picks out the value of function, continuous function f of x at x equal to 0. That is why you get f of 0. Okay, so you remember this property. This helps you to do problems easily. Okay, so if you need the value of a function at its origin, you can make use of this property of Dirac delta function. Okay, now here we discuss about the point origin x equal to 0. But suppose that our Dirac delta function centered about x equal to a, not about x equal to 0. Okay, the second property is related with that thing. Second property. Dirac delta function centered at x is equal to A. Okay. That means the Dirac delta function looks like this. I'll show here. Suppose this is del of x plotting along this direction and x is here, this is x equal to 0. At this point this is x equal to A. Okay, and our Dirac delta function is like this. Okay. This is the point A. This time the origin is shifted to A. Okay, this function is represented by del of x minus A. This is actually del of x, and so you can write this as del of x minus A. Okay, del of x minus A. Then x equal to A, it shifted to 0. Okay, when x equal to A, this is del of 0. Okay, so you can write here the Dirac delta function as del of x minus A. Now, if you multiply this function with f of x del of x minus A, what you get? This function, this product equal to 0 except at x equal to A, because at x equal to A this is del of 0. Okay, so I can write here this is equal to 0 except at x equal to A. This product equal to 0 except at x equal to A. So this you can write this f of x del of x minus A as f of A del of x minus A, because this function is not 0 only at x equal to A. Now you can integrate this thing just like as we do earlier. Minus infinity to plus infinity, f of x del of x minus A dx. This is equal to, substituting for this, you get f of A integral minus infinity to plus infinity del of x minus A dx. Okay, this integral is always 1, so you get here f of A. Okay, so now in this context you can see that since the origin is shifted to a point x equal to A, the Dirac delta function can be represented like this, del of x minus A. In this context, the integral f of x del of x minus A dx picks out the value of the function at x equal to A. Okay, the value of the function at x equal to A. This is another property which you can make use while doing problems, which helps you to find out the integrals easily. Okay. Now there is a third property also. The third property is connected with the limits of integration. Okay. Limits of integration. Okay, here the integration limits are minus infinity to plus infinity. Okay. For example, in this case, you can see that this Dirac delta function extends only this much. After that, it is already 0. Okay. So, if you write the integration limits like this, minus, suppose I want to just redraw this diagram. I can draw here. This is del of x, and this is x, and now this is x equal to 0 here, origin. Okay. Now this is the Dirac delta function like this, and this point is minus epsilon and this is epsilon. Okay, just showing the width of this Dirac delta function. Okay, in this context, integral minus infinity to plus infinity f of x delta x d of x can be written as integral minus epsilon to plus epsilon f of x del of x dx. Okay, because you can see that this size of the delta function is only up to epsilon. After that, it already 0. So, you can replace the integration limits from minus infinity to plus infinity to minus epsilon to plus epsilon, where this epsilon represents minus epsilon to plus epsilon represents the width of the Dirac delta function. Okay, minus epsilon to plus epsilon is the width of the Dirac delta function. Okay, Dirac delta function. These are the peculiar properties of Dirac delta functions. Okay. Now we can discuss. Let d1 of x and d2 of x are two Dirac delta functions, and they satisfy the condition integral minus infinity to plus infinity f of x d1 of x dx equal to integral minus infinity to plus infinity f of x d2 of x dx for all ordinary f of x or continuous f of x, then d1 of x and d2 of x are equal. This is called the fourth condition. Okay, these are the different properties of this Dirac delta functions. 4 properties. This condition should be held for all f of x. Then only you can treat these d1 and d2 are equal functions. Okay. Now, I think we can do a small problem just to confirm that we get the concept. Okay. Problem 1. Okay. Evaluate integral 0 to 3 x cube del of x minus 2 dx this is case 1, and the case 2 is integral 0 to 1 x cube del of x minus 2 dx. We have to check this integral. So we can do first the first integral, problem A. Okay. There it is given that integration limit is from 0 to 3 x cube del of x minus 2 dx. We already learned about f of x, del of x minus a dx. Okay. So in this context, f of x equal to x cube and a equal to 2. Del of x minus a equal to 2. Okay. So you can utilize the result integral 0 to 3 x cube del of x minus 2. Oh, you can write here. This is minus infinity to plus infinity f of x del of x minus a dx equal to f of a. Now you can compare here. You can see that this integration limit runs from 0 to 3 and its origin lies at 2. So no problem. This Dirac delta function lying inside this integral 0 to 3 because its origin is at x equal to 2. Okay, so you can write this as f of a. That means in this context, in the given problem, this is equal to, let it be I1. Okay, I1 equal to f of a equal to 2 raised to cube. This is equal to h. Okay, because x equal to f of a, x cube. So a cube, 2 cube. You get h. Now, the second part. In the second part, integration limit is from 0 to 1. Then what happened? Then you can see that this integration limit lying outside the Dirac delta function. So it is always 0. In this context, for b, integral 0 to 1 x cube del of x minus 2 dx equal to 0 because integration limit lies outside the Dirac function. Outside the Dirac delta function. Because you can see that here its origin lies at x equal to 2. Sorry, this peak value lies at x equal to 2. But your integration limits run only from 0 to 1. Okay. Now I think you have a picture how to use this Dirac delta function to solve